Okay, so here in section 10.5, we're going to be interested in summing up, if we can, the infinitely many terms in a geometric series. Now, obviously, if you have a geometric series, 1 plus 3 plus 9 plus 27 plus, that's going to sum to infinity, unless we're doing string theory, in which case we might get a weird answer. But for our purposes, indeed, we keep adding more and more terms, bigger and bigger terms, we add up to infinity. However, we learned in the end of section 13.4 that if we sum an infinite geometric series such that the ratio's absolute value is less than 1, our homework problems were such that we saw that the sum turned out to be T1 over 1 minus R. And we did that quickly in class and as a homework problem, and we'll just make sure that you have it here again. So that reminder is, let's suppose we have our infinite geometric, which means we have a first term, and to get to each subsequent term we multiply by r. So we get to our last term is T1 r to the n minus 1. We have a formula for the sum, and we derive that formula for the sum. It's T1 times 1 minus quantity, our ratio r to the n, over 1 minus r. And the question is, what happens if we let the limit of n head out to infinity for the sum of this series? And the idea is, well, the T1 is still there. That's fine. 1 minus, and the key element in here is the r to the n. What's going to happen? And clearly 1 minus r isn't going to, that's not very exciting as n goes to infinity. I certainly already have r, not really affected. The question is, what's happening with this r to the n term? And we learned that the limit, as n goes to infinity, of so my key here really is considering what's happening to this term right here as n heads to infinity. Clearly T1 is fixed, clearly r is fixed, not a big deal. The question is, what is this term doing? And we learned that the limit as n heads to infinity of r to the n will equal 0 if and only if that r, the absolute value of r, is less than 1. And again, that should make intuitive sense to you, because let's think about it. Let's suppose we have something, an r value like negative 1/4. If I look at what's going to happen if I take that negative 1/4 and I start raising it up here to bigger and bigger powers, the bigger I make my power, as a, remember, as a sequence, I'm plugging in positive integers, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The larger and larger I make my power, this number is going to get smaller and smaller. Now it may alternate negative and positive, but it's honing in on 0. And the bigger I make n, the closer I get to 0. And that's my key here. This term, the bigger I make n, it heads towards 0, so I'm left with a T1 times 1 minus 0 over 1 minus r, and that heads to our T1 over 1 minus r. So on one of the homework problems, I think last one maybe somewhere there, just a little helpful hint, is when a ball bounces, let's suppose I'm going to take a ball and I'm going to drop it from some height, and it's going to come down here and hit. Then it's going to bounce up again, and then it's going to bounce down. And again, I'm going straight up and straight down here. And then it's going to bounce up, maybe not so high again, but then it's going to bounce that same height down. So arguably, it would look something like this. Up, if I start from up here, it's going to drop, then it's going to bounce up to a height, and from that height, it's then going to bounce back down to the ground. So actually, if I want to know how far the ball's traveled, I'd have to count the up and then the down twice. So again, let's look at that once more. The ball's going to start, it's going to be dropped, it travels a certain distance, and then the first bounce, it's going to go up a certain amount, and then it's going to come down that same amount. So arguably for distance travel, I'm going to have 2 times that distance in there. So as you're thinking about the last problem, consider that hint.